For years, astronomers have known that the universe is filled with objects capable of reshaping everything around them. But few are as extreme as black holes. These enormous concentrations of gravity can influence stars, gas, and even the evolution of entire galaxies. Now imagine discovering one that appears to be moving through space rather than remaining near the center of its galaxy. That is where the story becomes extraordinary. Observations from the James Webb Space Telescope have helped astronomers investigate some of the most distant and violent environments in the universe. Webb's infrared instruments are especially valuable because infrared light can reveal structures hidden behind enormous clouds of dust and gas. Among the most fascinating phenomena studied by astronomers is a rapidly moving black hole associated with a long trail of material behind it. The remarkable part isn't simply the black hole itself. It is what appears to be happening in its wake. As a massive object moves through a dense environment, its gravity and motion can disturb surrounding gas. The resulting shock waves can compress clouds of material. Under the right conditions, that compressed gas can collapse under its own gravity and eventually produce new stars. In other words, an object normally associated with destruction could potentially be influencing the process of creation. Picture a gigantic gravitational engine traveling through cosmic gas, leaving behind a trail hundreds of thousands of light-years long. Along that path, disturbed material may become dense enough for stellar nurseries to develop. It sounds almost contradictory. A black hole consumes. Stars are born. Yet the universe often produces exactly these kinds of paradoxes. Black holes themselves are regions where gravity becomes extraordinarily intense. Once matter passes beyond the event horizon, it cannot return. But the environment surrounding a black hole can be far more complicated than the black hole itself. Gas can be heated. Particles can be accelerated. Magnetic fields can become highly energetic. And when a black hole moves through its surroundings, the disturbance can extend far beyond the immediate region around it. This is why observations of runaway black holes are so scientifically valuable. They allow researchers to study how enormous objects interact with the material between galaxies. And Webb's contribution is particularly important because much of this activity can be difficult to see using ordinary visible light. Infrared observations provide another window. They can reveal warm dust, hidden star-forming regions, and faint structures that might otherwise disappear against the background of space. But the runaway black hole is only part of the story. Another spectacular example of cosmic transformation can be found in a galaxy known as ARP 220. At first glance, ARP 220 might look like a distant glowing object. But behind that light is an enormous collision. Two galaxies once moved toward one another under the influence of gravity. Over hundreds of millions of years, their interaction distorted their structures, disrupted their spiral arms, and forced vast quantities of gas toward their central regions. The result was a violent galactic merger. And that collision triggered an enormous burst of star formation. Gas and dust became concentrated into compact regions where new stars could form at extraordinary rates. Webb's infrared vision allows astronomers to investigate these regions despite the thick dust surrounding them. What appears to be chaos is actually a complicated sequence of destruction followed by renewal. Old structures are disrupted. Gas is compressed. New stars emerge. Massive stars eventually explode, releasing heavier elements back into space. Those elements can later become part of another generation of stars and planets. So ARP 220 is not simply the remains of two galaxies colliding. It is a laboratory showing how cosmic destruction can create the conditions for something new. And when we place ARP 220 beside the runaway black hole, an even deeper pattern begins to emerge. The universe rarely operates in simple categories. Objects that appear destructive can influence creation. Violent events can produce new structures. And the death of one generation of stars can provide the raw material for another. But there is still another question. What happens when we look even deeper into this cosmic cycle? That's where the story becomes even more fascinating. The universe may appear chaotic, but beneath that chaos are physical processes that connect seemingly unrelated events. A black hole moving through gas. Two galaxies merging. A massive star exploding. At first, these events appear completely different. But they can all participate in the same enormous cycle. Matter is compressed. Stars are born. Stars eventually die. There remains enriched surrounding space. And that material can become part of future generations of stars and planets. This is one reason observations from the James Webb Space Telescope are so important. Webb is not simply taking spectacular pictures. It is collecting extremely faint infrared light that has traveled through space for millions or billions of years. Every photon carries information about the conditions that existed when that light began its journey. When astronomers examine distant galaxies, they are effectively looking into the past. And some of those ancient environments are extraordinarily violent. ARP 220 is a perfect example. The galaxy's unusual appearance comes from its history as a merger between two large galaxies. Gravity pulled the galaxies together and dramatically reshaped them. Their outer structures were stretched into enormous tidal features while huge quantities of gas were driven toward the central regions. That gas became fuel for intense star formation. Within the merger's compact core, enormous numbers of young stars can emerge from dense clouds of material. But star formation is only one stage of the cycle. The most massive stars live relatively short lives. Eventually, they explode as supernovae. These explosions are incredibly destructive on a local scale, but they also perform an important cosmic function. They distribute heavy elements into surrounding space. Elements created inside stars or during stellar explosions can later become part of new clouds of gas and dust. Eventually, those clouds may produce additional stars and planetary systems. So the death of a star can contribute to the birth of something that did not exist before. The same principle helps explain why the universe becomes chemically richer over time. Early generations of stars contained mostly hydrogen and helium. Later generations formed from material enriched by earlier stellar activity. The atoms in planets, rocks, and even living organisms were forged through ancient cosmic processes. This means that the universe is not simply expanding. It is evolving. And the runaway black hole adds another fascinating piece to this picture. If a massive black hole travels through a region containing dense gas, its movement can generate disturbances in that material. Shock waves can compress clouds. Compressed clouds can become unstable. And unstable clouds can collapse to form stars. The black hole itself may not be creating stars directly. Instead, its movement could alter the environment enough to make star formation more likely. That distinction is important. It shows how cosmic systems can interact without fitting into simple categories. A black hole can still consume matter while simultaneously affecting its surroundings in ways that may encourage new structures to appear. This is the strange duality of the universe. Creation and destruction are not always opposites. Sometimes they are connected stages of the same process. The observations of Webb are helping astronomers explore these connections with unprecedented sensitivity. Infrared light can pass through regions where visible light struggles. Dust that blocks an optical view can glow brightly in infrared wavelengths. That allows researchers to study hidden star-forming regions, warm material, and complex structures surrounding distant galaxies. And as more observations accumulate, our understanding of cosmic evolution becomes increasingly detailed. Galaxies collide. Gas clouds collapse. Stars ignite. Massive stars explode. Heavy elements spread outward. New clouds form. And the cycle begins again. Even the most violent events can become part of this process. That is perhaps the most remarkable lesson from these observations. The universe does not have a simple beginning and ending structure for every object. Instead, matter is constantly being transformed. A galaxy can be disrupted and eventually become part of a new galactic structure. A dying star can release elements that later become planets. A black hole can reshape the gas surrounding it. And a collision between galaxies can trigger an enormous wave of stellar birth. From our perspective, these events may look catastrophic. But on cosmic timescales, they are chapters in a much larger story. The James Webb Space Telescope is allowing us to see those chapters more clearly than ever before. And the deeper we look, the harder it becomes to describe the universe as simply peaceful or violent, creative or destructive. It is all of these things at once. Darkness can lead to light. Collapse can lead to formation. And destruction can become the beginning of something entirely new.